Swayam Prabha. Digital India. Educated India.
So we'll come to this part of the lecture on the measurement of soil water content. This is a continuation of our lectures on soil wetness. We discussed about various different ways that you can describe soil water contents. So we mentioned that there are two key questions that we want to address when it comes to soil wetness. The first one, of course, is this: how much water is present in soil? And we also mentioned that the simple definition to that is that how much water a soil has, per unit either mass of the soil or the volume of the soil. And so when it comes to the gravimetric water content or mass basis, the gravimetric water content with which we call theta with a subscript g is the mass of water or unit mass of the dry soil. And this dry soil has to be soil which is dried at 105 degrees centigrade for a period of 24 hours, so that there is no free water present in soil. Mostly whatever water small amount that is there are in the adsorbed phase or in form of the bound water. And so all that excluding the bound water at 105 degrees centigrade, all the water gets evaporated and diffused out over a period of 24 hours, and so leaving the dry soil. So this gravimetric water content is defined in terms of the mass of the dry soil, and not in terms of the moist soil weight, because if you take moist soil weight in the denominator, what would happen is that then depending on how much water is present, the denominator would also change while the mass of water itself is changing. So an intrinsic or inherent intrinsic quantity for the soil wetness will not be possible. And so it's always mass of water divided by mass of the open dry soil, which does not contain any water. And to get a soil wetness in terms of volume basis, you basically multiply the gravimetric water content with the ratio of the bulk density to the water content, right? So one of the things that we are going to discuss in this part of the lecture is what sort of methods are used to measure this water content. And when it comes to measuring soil wetness, this is one of the very important parameter when it comes to managing a crop, because water and nutrients are two major inputs for a crop, and so therefore any agricultural, at least the crop production components, requires that we must really manage this important resource in a very efficient manner. We talk about all kinds of requirements, producing more crops per drop of water and so on and so forth. And fundamental to this is that we must have the ability to measure soil wetness. And as I would go through some of these slides, you would recognize that measurement of soil wetness could become a very, very expensive expensive aspects of water management. So let's get into some of the methods of measuring how much water is present. And so if you look at these methods, you can essentially divide them into two parts: the direct method and the indirect methods. In the direct method category, there is only one, which is the measurement of gravimetric through the sort of thermal approach, where you basically dry the soil, as I mentioned, at 24 at 105 degrees centigrade for 24 hours. And there are a bunch of indirect methods, and we'll go one by one, and so that you have a good feel for how soil wetness is measured. So gravimetric method, as I mentioned earlier, it's very simple. You go measure the weight of the moist soil, and then of course you dry it, putting it in an oven at 105 degrees centigrade for a period of 24 hours. Take the oven dry weight, subtract out these two weights, and then divide that with the oven dry mass of the soil, and that gives you the gravimetric water content. Of course, the drying process can be a bit different. It may be possible to dry the soil using maybe some kind of an infrared heater, or you can remove the water using a microwave. But this, for the whole purpose is that you need to remove whatever free water is present, and so whatever method that you choose, it's a laboratory based method, has to be a laboratory based method. So you have to have some kind of a drying equipment, and as of today, the gravimetric method still is the standard method, against which all remaining indirect methods are being compared. The method itself, you have certain advantages and certain disadvantages. The method is direct. Of course, you really go out there and take the soil and dry it out. There is nothing indirect about it. You measure the wet loss because of the drying process. It could be, of course, inexpensive. All you need is an oven and a balance. Method is pretty accurate, and you don't need any. It's a direct method. Don't need any calibration, or so that no standardization is necessary. So the method is very robust. Certain disadvantages to that, due to this, is that you still need to really spend 24 hours in the laboratory to dry the soil, and that could be some time, depending on what kind of oven and all you have, that can be time consuming. Depending on number of samples that you analyze, this whole process could be very labor intensive. Imagine that you have to really collect samples from so many fields. For instance, in a village, you have to really take out soils from every field, and to measure at every location, and these could be very labor intensive. Soil collection as such is a very labor intensive and tedious step. The method is destructive because once you really remove a chunk of soil for making this dry wet measurement, that soil is lost. So you cannot go back to that same soil itself, and then you want to change. You want to know how the water content change in that sample. It's not possible. Of course, you could really take a sample in a nearby location, but then because of the variability of the soil that we discussed, it may not be possible for you to really have exact same nature of how soil wetness changed over a period of time because of the variability. So it's destructive measurement, makes it inconvenient, for sort of monitoring and to know the temporal changes, the dynamics of the soil wetness, how it changes with time, and also space, because you cannot cover the whole area. Very labor intensive. Discrete measurement, so that's coverage of the total area is almost impossible. Just can take so many samples, and there will be distance between two sampling locations. No automation is possible because after all, you have to really take that soil and then move it to somewhere in the laboratory to do that measurement. The method continues to really enjoy as the standard method of measuring soil wetness till date, because it's a direct method and a very accurate method. Nevertheless, sometimes you need to really be also careful, because many a times during collection of the sample and putting it in a moisture can, for example, you may and handling it and taking it to the laboratory, you may lose substantial, depending on how you are really doing it, you can lose substantial amount of the moisture during transport, and unless you really cover it. So you need to be very, very careful about collecting the sample and then putting it in sealed or airtight containers, so that there is no loss of water even in the paper page. So therefore there are certain limitations, but overall you can think of these to be the standard method against which all other indirect methods are being compared with. The next one that we talk about, and the way I have planned this presentation, I would really go from probably the more expensive methods to the cheaper methods, and obviously as the method changes, there will, and these are all indirect methods, so therefore each one of them have certain amount of limitations and some certain amount of advantages, and we'll discuss about each one of them, and hopefully sort of resolve that depending on what our availability of the funds and our requirement, we would be able to adapt one or the other method. So this group of methods are having this root in the radioactive decay. So neutron probe basically works with, it's an indirect method. So what it is here, it is done is that this thermalization of the fast neutron by the hydrogen atom present in the water molecule is used as a principle. So typically what is done is that about 10 to 50 millicurie of americium 241 basically it's used with a mixture of beryllium in a radioactive device, and so what happens is americium emits these beta particles which interacts with the beryllium atom and releases very fast neutron, and these fast neutrons have very high energy, about 2 to 4 million electron volt. They travel with they're very fast, 1600 kilometers per second, and these fast neutrons typically with such high kinetic energy, when they collide with the different atoms, typically most collision processes are elastic, means they do not lose much of their energy, except when they really come across atoms of similar mass, for example hydrogen and the neutron having similar mass. The collision is inelastic, and so multiple collision takes place, and in the process they lose their substantial amount of energy, and come down to the energy level as low as about just 0.03 electron volt, and these become very slow with just a velocity with a speed of about 2 to 7 kilometers per second. So typically the availability of the hydrogen atom, which is from the water, higher the amount of water present, more hydrogen atoms are available to thermalize or slow down these fast neutrons. So therefore, that measure of how much a particular how many neutrons are thermalized, compared to how many neutrons you started with. So that sort of a ratio of the slow neutron to the fast neutron after the collision process should be proportional directly to the number of hydrogen atoms present. So that's the principle. That indirectly, you are looking at how many fast neutrons you have released, and how many of them thermalized because of how many hydrogen atoms you have. So that's how it is. It is an indirect method. Now, hydrogen, and typically, in addition to that, there are other atoms such as carbon, cadmium, chlorine, also, are able to thermalize the fast neutrons, but because their relative the number in the soil is less, therefore, you could say that mostly it is the hydrogen atom present in the water molecule is responsible for thermalizing the neutrons. So therefore, a lot of calibration is needed, because in a specific soil, because depending on what kind of composition that you have, you need to really build these relationships between the soil wetness and the relative number of the slow neutron to the fast neutron, and we call that as a count ratio. So the count is basically the number of slow neutrons, and standard count is basically the number of the fast neutrons you released as the radioactive source is activated. And so water content essentially is used as a linear function of this count ratio. So once you have several measurements of the soil wetness in a given location using this gravimetric method, and then you also, for the same soil, for different wetness, you estimate the count ratio using a neutron source, and then you can build some kind of a calibration curve. In other words, you can estimate these coefficients A and B, and so therefore, once you know all these, in an unknown location, you measure the count ratio, and you know already A and B, so you should be able to indirectly measure the water content. So that's the idea. So the whole thing is packaged in something called a neutron probe, and it has got basically a sealed source up here, which has got this mixture of americium and beryllium, so that's the source. Also, it has got a detector, and so basically that source and detector assembly has to be lowered into the soil, and the way it is done is generally in the field you have to put an aluminum access tube, and basically an aluminum pipe, which should have the inner diameter of the aluminum pipe should be same as slightly larger than the diameter of this probe, this neutron probe, and so typically the fast neutron would pass through the aluminum elastically, basically, without losing any kinetic energy, and sort of as they really move out, heat this water molecule, and sort of each inelastic collision, so therefore really create this slow neutrons, and the detector, which is there near the source, and should be able to detect this neutron cloud. And so before you really activate or lower this neutron probe into the aluminum access tube, you need to really make the measurement of the standard count for this equipment, because continually, naturally, this americium would decay. So the standard count changes from time to time. In fact, always it's sort of, the source is getting decayed, and so therefore the standard count would change. Number of fast neutron it can really produce gets reduced over time. And so you need to really get the standard count measured before you really do this measurement. And so once this thermal neutrons are measured using the detector, you come out and say, I can really have a count ratio, and this count ratio is then, of course, is fed into this equation, the standard curve that you have generated earlier in the calibration process, and should be able to then get water content measurement. Now, one of the this whole system really measures whatever water molecule, whatever source of the hydrogen is present in the soil, in and around this this some kind of a volume of measurement, whatever is there in that soil volume till the fast neutron kind of reach out to thermalize, so that water, all those slow neutrons are going to be measured in that volume. So the issue here is that the volume of measurement, even though it is a volumetric measurement, the volume of measurement would depend on how wet or how dry the soil is, and this volume, the radius of that measurement volume is observed to be about 15 times that water content raised to the power 1 over -1/3. And so with a very wet soil, typically you are going to see that your volume of measurement is small. So you are measuring a smaller volume, water content in a smaller volume, whereas in a dry soil you are measuring in a larger volume of measurement, and that really gives you uncertainty about where you really measured water. And that's one part of it. The second part of it is that because there is a volume of measurement involved, generally you couldn't really activate the radioactive source near to the surface of the soil. You need to really, these are fast neutrons, very high energy, and so you don't want to really stay close to the machine. So generally what is being done is that the machine has to be lowered into the soil, so that hydrogen atom present in the water molecule would really thermalize them. Otherwise, this high energy would strike you. And so therefore it is the machine has to be, the probe has to be lowered into the soil. Surface measurements are not possible with this. And so only depth-wise measurement. Now, other thing is that because you need an aluminum access pipe to lower this probe to measure water content at different depths, so therefore if you are to really go out to a field, an agricultural field, and you have a bunch of aluminum access tubes installed in the field, almost like a permanently installed, all agricultural operation become very, very difficult. Other than this is a radioactive source, you need to really certification. You need to really also have certification to be as an user. You have to be certified. You have to have certification to really move from one location to the other. And so these kind of technologies are now getting obsolete from our from time to time. The next set of no, this another important aspect of these neutron probes are that as the soils typically have different bulk densities, you will notice that in the same soil, you could have different densities depending on what is the level of compaction. You can see that the volumetric water content as a function of the count ratio, those linear this linear standard curves depend on these densities, and so one of the things is that the condition of the soil would change the standard curves, and specifically density is a very kind of a variable quantity. Bulk density is not an invariant condition, a property of soil. So as the density changes from time to time, you need to really have a different standard curve, and that's not very, very convenient. And so some of the to summarize, some of the advantages are, of course, this is not a completely destructive sampling, right? Because you don't need to really carry the soil to the laboratory in the same field condition. So it's a kind of a field condition, giving you the soil wetness in that entire profile, without having to really dig out the soil and take the soil to the laboratory condition. So that's strong advantage. The method is, depending on how you do the calibration curves and how frequently you do the calibration curve, the method is fairly accurate. The errors are in the order of about less than 8% in accuracy. Well, that's still a large error, but it's admissible when it comes to the field condition in an agricultural application sense. Disadvantages are, of course, you need calibration. And calibration in the same site multiple times. Sometimes even calibration is, people have used different calibration curves depending on what is the stage of the crop in a particular field, and that's pretty time consuming and cumbersome. Near surface temperature, most of the crops, the root zone is top 30 centimeter of the soil. The agricultural crops, food crops, for example, rice, wheat, the root zone is maybe top 30 centimeter, and you won't be able to take measurement in the top 15 centimeter of the soil. Minimum, you have to lower the probe below 15 centimeters so that there's no fast neutrons coming out and hitting you. So near surface measurement is not possible. Hazards, as I mentioned, the licensing necessary to use it, to move it from one location to the other, and you just cannot really have a neutron source out there unattended. Automated measurement is not possible, because each time physically one has to go activate the neutron source and lower the probe from the shielded device. And so these are some of the big disadvantages. So to me, the biggest one is the hazard associated with it, and certification, and of course, no automation is possible. See, the next range of measurement methods for soil wetness is the electrical methods, mostly the frequency domain and the time domain methods. So here, the basic principle is that if you really pass electromagnetic waves through the soil, water being a dipole, polar, you would see that it it would get polarized because of the electrical field, and you change that electrical field, it would really show you a change in the its polarization characteristics. The velocity of the electromagnetic wave would depend, as water being a dielectric material would depend on the bulk permittivity of the soil. As all of you know, the relative permittivity or the bulk permittivity is the ratio between the permittivity of the material and the permittivity in the free space, and so generally, when soil is the dielectric material, with water being the major dielectricum, so what you generally have is that the soil is completely dry. For example, silicon dioxide, for example, the quartz, the dielectric constants are in the order of about 5. So depending on the composition of the soil, the dry soil has a dielectric constant of about 5 to 10. Air is about 1, water is about 80, and so when you have a mixed medium, you could get the dielectric constant of water, dielectric constant of the soil, dielectric constant of the air, and so you could set up some kind of a dielectric mixing model to back calculate, what is the dielectric constant of water, or what is the, how much water is present from the bulk dielectric constant measurement, right? And so generally these electromagnetic waveguides are used to allow the electromagnetic pulse to really travel through those waveguides, and you would in the process, the materials surrounding those materials surrounding in that electromagnetic field would really show that polarization. So water mixture, and where water gets polarized, and so in the process you will be able to see a change in the overall dielectric permittivity, dielectric constant of the soil. So you will have a bulk dielectric constant of the soil, and so in about 70s, people started playing with this approach, and it almost started sometimes in 1930s, when people tried to install the electric poles. They noticed loss of their loss of energy, and so a lot of studies were done by the electrical engineers about how this polarization affects in the ground and in soil materials mostly. And so those really came out to be several measurements, and it was noticed that if you're kind of working in the megahertz range, for instance, your frequency is about 700 megahertz, you see that the volumetric water contents for soils with different different soils have sort of a very smooth change in the soil wetness, because and leading to the dielectric constant. So the first one that you see on the left you are seeing the real part of the dielectric permittivity, and in the right hand side you get the imaginary part. As the bulk, the relative dielectric or the dielectric constant is the sum of the real part and the imaginary part, and so you can see that there are as you change from one soil to the other, these curves are kind of a little farther away, and if you increase the frequency from 700 megahertz to about 1.4 gigahertz, you see that these dielectric constants with volumetric water content. It's kind of specifically you see that this imaginary part is now becoming very close to each other across different soil types, and you increase further from 1.4 gigahertz in the left and go to the 5 gigahertz level, you see that most of these different soil types they're kind of coalescing, and kind of merged with each other, telling us that you probably can use just a single relationship between the dielectric constant and volumetric water content across different soil texture, and should be able to use it for estimating as an indirect estimation process for volumetric water content from dielectric constant. Well, this is what is the people have seen increasing that frequency to even higher frequencies into the gigahertz levels. You see that once you go from 700 megahertz, there are differences between these curves, and then goes to 1.4 to 5 to 10 to 18 gigahertz. You can pretty much see that a single relationship between the dielectric constant and volumetric moisture content. And here actual measurements are made, dielectric constant for different these symbols that you see for different soil types with water content, and you could see that almost across different soil type, the relationship between dielectric constant and water content is unique. And so these sort of measurements in 70s really led to development of soil moisture sensors based on the measurement of the dielectric constant, where you can have simply a simple, maybe polynomial form of this equation, or some kind of a power form of the equation, relationship between the volumetric water content and the dielectric constant. And this equation up here is one of the most the first one given by Professor Top and from Canada in 1976, famous Top's equation between the dielectric constant of the soil and the volumetric water content. And so typically what is done is that in the design of these kind of sensors, you have some kind of a waveguide through which an electromagnetic pulse is passed through, and the extent of this dielectric relaxation is measured in terms of the velocity of the pulse passing through the waveguide, and the dielectric constant is using the thin disk kind of approximations. It is shown that the dielectric constant can be a square function of the ratio of the velocity of light to the velocity of the electromagnetic pulse in a dielectric material, so C over V. And this velocity is basically what is the distance that electromagnetic pulse travels inside the soil over time. So this is kind of because it's a waveguide, so basically you have a pulse going certain distance, and as the waveguide is there's no more waveguide, sort of comes back to the signal generator, so that you have like twice the length over time, and that's the velocity. So the ratio of the speed of light C to that velocity in an unknown sample is measured to get a bulk dielectric constant of the soil. And once you know the dielectric constant, it's easy to use this Top's equation or the other one, a power function relationship, to get the volumetric water content. Okay, this whole thing in about 90s and in 2000s, one of the device which is used to detect fault in the cable lines, which is called a time domain reflectometry, a cable tester from Tektronix used to be used for measuring this, this dielectric relaxation in soil. So basically, what we would do is that you will have a probe, some kind of a, sort of a stainless steel rods are joined together and connected to the coaxial cables connecting to the oscilloscope here, and you sort of look at how this signal move through the probe, and then sort of passes, as it passes through the soil, you lose part of its energy, which is being utilized to really polarize the water molecules, and then as this electromagnetic pulse really reaches the end of the waveguide, it would really come back. And that is how this, you have this twice L over T as the velocity of that pulse. And so you could estimate this velocity, and then taking the ratio with the speed of light and then squaring it, you get the dielectric constant. And this used to be the scenario in 90s, when we will just take this cable tester from the telephone industry to measure the soil wetness. But things have changed. We have now soil moisture probes using this time domain reflectometry. There are a bunch of them are available now. The handheld ones, you could do automation with this because of the electrical nature, and so some of the advantages are the sample volume. The TDR probes typically are about 10 to 15 centimeter long, and the distance between two probes is in the order of about 1 centimeter. So typically around 2 to 3 centimeter sampling volume, all you need to really insert a probe. And so you should be able to measure every 3 centimeter from the soil surface, so you could almost do a near surface soil wetness measurement using this technology, the TDR, or the time domain reflectometry technology. The measurement are very fast. The whole process takes in the order of about 50 milliseconds to take the whole measurement. And the frequencies operating in these TDR probes are at about 3 to 16 gigahertz range. Because that's where these differences in soil textures would go away, and so you can just use a single calibration curve, just like a factory installed calibration curve you could use. Measurements are fast because of the electrical nature. You could do this automation, but in the hindsights are, you still have to really put the probe in the ground. So imagine that you are looking at the soil wetness in a deeper soil, and you need to really dig out a pit and then sort of insert the probe, and then because you need to have a physical cable that really goes from the probe to the your oscilloscope or the controllers. And nowadays there are simple controllers available. And so all these, for example, in this is a Campbell Scientific one, and all these your circuits are embedded in this whole those probe holder, and you basically have a readout device up here, and so no, it's not quite convenient to take the deeper soil measurements. So although sometimes these days also you can have a very long probes, like to a depth of about 1 meter, probes are also available, but the normal probes are around. It comes with two versions, 12 centimeter and 20 centimeter, for example, from the Campbell Scientific. One of the other big thing is that one of the because of their electrical nature, if you are having a salt affected soils, you need to ideally have different kinds of calibration, and of course the major constraint is the cost. Even today, the time domain reflectometry meters are expensive. They would run to somewhere around 2 to 3 lakhs a piece, a handheld one, and automation, of course, it's going to be more expensive. Where you have to have multiple probes and all multiplexed to cover large areas. They're still non-destructive, near non-destructive. Automation is possible to a large extent. So remote measurement will be possible. Measurements are very, very fast, but continue to be expensive. But one of the important part is that they are still very, very accurate. Measurement is possible, although sometimes you could really get overestimation, specifically in the dry end of the soil wetness. Okay, anything which goes close to accuracy to the standard method in the gravimetric method is the time domain reflectometry, but they are one of the still very expensive approaches like the neutron probes. You could also get a cheaper version of the capacitance, this kind of probes, where you really work in not in the megahertz, not in the gigahertz range, you work in the megahertz range. So you measure the capacitance of a soil as a function of the, as you know that because the signal generators for low frequency in the even the megahertz level are cheaper. These probes can be cheap, can be very inexpensive, but the issue would be, as you notice that in the megahertz level, the soil specific calibrations are going to be absolutely necessary. So therefore the accuracy problems are a big problem with this, and the cost, of course, are a lot lower than the time domain reflectometries. These probes are also designed for non-destructive measurement. They are also good for automation, and many times we really look for relative soil wetness. So once you really install a probe at a particular location, you should be as long as you have a good calibration, you should really be able to still have a relative, look at the dynamics of the soil wetness, so how it changes with time, that you could really monitor using capacitance probes, even though they really suffer from accuracy problems in the order about 10% errors in the capacitance probes. Okay, so these are the expensive part of the probe, still running into somewhere around 50,000 rupees to a few lakhs. And if you're going to a neutron probe, you're probably going to something like about 10 lakhs, and they're getting obsolete now. Let's look at some of the easier ones, inexpensive ones, which are becoming very, very popular. Those based on simple electrical conductivity or thermal property measurements. Two specifically are on the electrical conductivity probes and the heat pulse probes. One really uses the electrical conductivity of the soil. So when you look at electrical conductivity of the soil, for example, the electrical conductivity of the bulk soil, if you are looking at it, should be a function of the electrical conductivity of the dry soil, and it should be very, very small compared to electrical conductivity compared to the soil solution, because soil solution has all the electrolytes. They really contribute to the electrical conductivity. The electrical charge, which is basically your cation exchange capacity for soils, for a given soil, of course, it remains constant. So if you do the calibration, it should be all right. So that relative change in the soil wetness still you can really measure using very inexpensive electrical conductivity probes. One of the difficult aspect of the electrical conductivity probe is the geometry. Imagine that when the soil becomes unsaturated, and so you have this water present or the electrolyte solution present, in the soil pore network. So as the soil would lose water, the water, wherever water is present in soil, that geometry is going to change. So therefore, electrical conductivity probes would really have three components. One is the electrical conductivity of the dry soil, electrical conductivity of the soil solution, which would be a function of the soil wetness, like how wet or dry soil is, and the geometry of that whole setup. In that also would depend on the soil wetness. Similar to electrical conductivity, we can also have the heat capacity measurements. And if you look at the heat capacity again, soil is a three-phase system. You have the dry mineral phase and organic. Maybe you have some solid phase from the soil organics, and you have, of course, water, which is the soil solution phase, and then you have air. And the heat capacity of air is the negligible one. And so we look at these two different approaches. For the electrical conductivity probes, there are several electrode arrays. Different configurations are available, and the most popular one is the Wenner array, where four electrodes are positioned equidistant from each other. And so what generally is done is that an excitation voltage is applied, across this outer two electrodes, and basically the soil which is present in between these probes, acts as a sort of a resistor. It's just, if you imagine, it's kind of a pseudo resistor, and so as this excitation voltage is applied across these two outer electrode, you will see that there is a voltage developed between these two inner electrode, this electrode number 2 and 3. And so again, a sort of a bridge measurement can be designed, where you have a known resistor R2, and so if you have a constant current source, you should be able to get the ratios of the two voltages as the equal to the ratios of the two resistors from the Ohm's law, and so basically, you will measure the voltage V2, you will measure the voltage Vs. You already know the resistance R2, so that's a standard resistor, and you know how much voltage you have S you have applied, and so the only unknown is this Rs, which is the resistance offered by the soil itself. And so getting that resistance of the soil, you should be able to really do a calibration between the resistance of a moist soil at different soil wetnesses, and should be able to look at a calibration curve which sort of looks like this. Here I show for two different kinds of electrolyte solution we have used. So known electrolyte, and you see that the volumetric water content as a function of the bulk electrical conductivity. You see that the moment the nature of electrolyte changes from potassium bromide to calcium chloride, these relationships differ. And if you look at soil as a it's kind of a complex cocktail of different electrolytes, you would really tend to wonder, whether a bulk electrical conductivity would have a unique relationship with the volumetric water content. But nevertheless, if you are to really make a 4-probe electrode, you probably have, just have to spend something like, 20-30 rupees, and should be able to have a electrical conductivity probe by soldering them, and then have some kind of a probe holder, and then you insert them into the ground, and should be able to measure electrical voltages, and set up even a more sophisticated bridge measurement into the and then have a full-blown device, easy to make. The only problem with that is that they will have huge amount of the errors because of the changes, the dynamic nature of the electrolyte concentration, different kinds of electrolytes used. So that's kind of the hindsight, but extremely cheap. It's possible to do automation easily, because there you are measuring electrical measurement, remote measurements will all be possible, and all that advantages come with the electrical conductivity based measurements. The heat capacity based measurements are more robust than than the electrical conductivity based measurements. As I mentioned, the heat capacity, again, just like the dielectric mixing model, you could really set up a mixing model for the heat capacity of the bulk soil. So as you all know, the heat capacity is the energy needed to raise the temperature of unit mass of the substance. So you look at soil as a multi-phase system. You have the solid phase, and you have the water phase, and you have the air phase, right? And you could have, again, when it comes to the solid phase, you can have the organic matter and the mineral soil fraction. And so, depending on what volume fraction of air you have the specific heat capacity of the specific heat or volumetric heat capacity of the air, and you have the air fraction, volume fraction of air. So this bulk volumetric heat capacity. So heat capacity of the bulk soil will be the sum of the volumetric heat capacity of the air phase, the organic matter phase, the water phase, and the mineral phase, each weighted by their respective volume fraction, right? Well, that one is negligible. Air is very small, so that goes to 0, right? You could know how much organic matter is there, right? And you can, from the tables, you can find out what is the heat capacity of the organic matter. It's about 0.6 calories per centimeter cube per degree centigrade. You already know the heat capacity of water is unity, and you know the heat capacity of the mineral phase, which is 0.48 calories per centimeter cube per degree centigrade. So therefore, you have this volume fraction of water. So this is actually the volumetric water content, theta, right? Theta V, whatever you call it, right? Theta V. And so essentially, therefore, if you measure the bulk soil heat capacity, right, and you know these volume fractions, you see this F0, right? F0 and FM, so they are essentially equal to 1 minus porosity, right? 1 minus porosity, right? So volume fraction of pores, and these are the volume fraction of the solids. And so you need to know also the porosity. That means you need to know the density of the soil, bulk density of the soil, and then knowing particle density to be 2.65 gram per centimeter cube. You will be in a position to estimate what is the water content of the soil. And so Again, this is a very easy method. The way it is done is, you know, you have a heating element inside one of the probes. You have some kind of a temperature sensor here, and so basically you do the heating up here, and upon hitting heat energy would radially move from the heater towards the temperature sensor, and so through the soil, and so so you will have some kind of a change in the temperature, and the way you really do this heating, and typically if you do a pulse heating, that means you heat it for a fixed amount of short amount of time. It's about around 6 to 8 seconds, and then you cut off that energy source. What would happen? You have a source, constant source, and then you shut it down, and so therefore your temperature response is going to really, the temperature would increase, and as the source is cut off, now it's going to come down, and this is how it looks like, depending on what sort of soil wetness you have. The temperature difference from the ambient, the starting temperature, to the rise in the temperature because of the heating, in the order of about, if you're doing about 6 to 8 seconds of heating, typically you get about zero point 0.5 units of change in the temperature, and so you will see a sort of a temperature time curve, and getting these temperature maxima, and the time to really reach that temperature maxima can be used to indirectly estimate how much water content is there, and there is a relationship. And again, these are indirect relationships, right? These are indirect methods. So you sort of estimate the water content from indirect measures, like in this case, the temperature maxima as an inverse function of the volumetric water content. So what we have done in this class is that we talked about different methods. We introduced different methods of measuring the soil wetness, and we noticed that each one of them has each one of them have their relative advantages and disadvantages. These methods have been used over last 2 to 3 decades, and specifically because of their accuracy issues, because of their cost issues, people choose one method over the other depending on the resources they have. You could notice that none of the methods, including the standard method of estimating the soil wetness, come any close to how a typical say grower, for example, or a farmer could really use them conveniently and in an inexpensive way. And so this is one area which still requires a lot of development, and we are making some fast movement. Our signal generators are becoming cheaper. Our dielectric property-based methods are becoming slowly less expensive, but we still have a long way to go. One of the other method, which is sort of I didn't discuss much, is can we really measure this soil wetness or the dielectric properties of because we are talking about these megahertz and the gigahertz region. That's the microwave region, right? We have quite a few microwave sensors in our satellites, and so one of the things that we are kind of in a research and development phase is, can we use these microwave based sensors that are present in our remote sensing satellites to monitor the soil wetness, and there is a lot of research going on. There's a lot of development going on, and Primarily, the advantage is that you could really measure the soil wetness for a large area, and you know uh, and in very less time. And so these methods, we hope that be available some more, so that you can pursue, maybe purchase some kind of a digital product, soil moisture product for your agricultural field, and that would make it more convenient. So again, this measurement of soil wetness or the soil water content is an area requiring a lot of our attention. We need cheaper sensors, and something that a farmer can use, you know, and only then only managing the soil wetness would be easier. Okay, thank you very much.